understood that it does not want me to say much, but there are three basic things I would say. First of all, Prof Atangana is a professor of mathematics at the Free State University in South Africa, and is the academic head of department at the Institute for Groundwater Studies, Faculty of Natural and Agricultural Sciences. Prof Atangana is of Cameroon origin and is really a prolific mathematician, a mathematician who has been able to connect theory and applications, and with important involvement in about more than 10 journal of higher caliber where he's in the editorial board. And I don't want to tell you the number of papers Prof Abdon has already published, but what is really important is what he has been able to achieve. You know, when we do research, we publish and people read our publications. Now, when people read our publication, they cite our publication. And this really show the importance of the publication we do, the impact we have on other researchers and students. And Prof Atangana happened to be recognized among the top 1% of scientists on the prestigious Global Claveret Web of Science list, which means that this is among the 1% best scientists in the world. And this is the first time you see an African reaching such standards. We are really happy, me first, to know personally Prof Atangana, happy that he's an African, and happy that he could find time to deliver this talk to such important and large audience. I insisted on Prof Atangana giving a sort of introductory talk on what he's doing so that he can encourage and invite the junior generation to do research in his domain, and maybe why not to be his master or PhD student in the future, so that he can train Atangana 1, Atangana 2, and Atangana 3 before he get retired. So having said that, Prof, once more, thank you for having accepted to deliver this talk. I'm really happy as Chief Academic Officer of the EMS Global System that you could do it, and I'm happy to give you the floor, and we are ready to listen to your discourse. Thank you. Bubakar, has Prof Atangana dropped again?
Yes, he dropped his back, but he's not sharing his screen or his video.
Prof Atangana, can we share your screen? While waiting, let me say hello to Franca.
Franca's probably stepped out too.
Oh, she's there.
Okay.
So what do we do?
Okay, there you go.
Okay, it's coming. Yes.
I have a problem of connection. As I told you, I'm I'm in a a forest. They call it hazel view. I come in the middle of a forest. I'm here for a holiday, but I decided to do this presentation because this is important for us. Can I start?
Yes, please go ahead. You have the floor.
Can I start?
Yes, please go ahead. You have the floor. Yes.
What is this? Hello?
Yes, go ahead.
Yes.
We're hearing you clearly.
Okay. Can you see my presentation?
Yes.
Yes.
Yes. Okay. So, yes, I'm very grateful for you giving me this opportunity. Sorry. Okay. So, I'm very glad that you get present to Africa also about fractals. So I would like to start with some real world problem. I had a discussion with my so they throw the body, then we want to actually know the mass of that person as function of time. So what happened is that you realize that the decay of the flesh of a human being will go very fast, but when it reaches the bones, if you want to actually model the rate of change of the mass, you will realize that for the first time, the mass will reduce exponentially, and the later time, the bones will decay very slowly. So there is what they call a crossover from a fading decay to a slow decay. So if we can also talk about another problem that we are speaking about the GL. For those who are driving Mercedes, you will realize that there is a specific type of cruise control in GL. What happens is that when you put the cruise control, the car is able to stop. If there is a car in front of it, then go back and remember the initial velocity that you give it. So that type of cruise control is different than the other cruise control in other people's car, where when you put the initial velocity, that initial velocity will allow you to go, the car will not stop or unless you break it. Whereas with the GL, what happens is that whether you remove your leg from the brake, but the car is able to do the job itself. And that is what they call non-locality. Let us take another example of a fly. Assume that I'm flying from maybe South Africa, then I want to go to Germany. Then I will tell my friend in Germany that I will be there at 12:30. According to what is written in my ticket, I can be there at 12:30. Why? Because if there is no disturbance, if there is no thing that will hinder the plane, I will arrive at a particular time. However, if there is a storm, for example, I will not be able to arrive at that time. I will have a specific delay. So I can also speak about the flow of water. When the water is flowing from the matrix soil and it reaches the fracture, it changes the speed. because in the fracture, the water goes to the high velocity, whereas in the matricoid, the water goes with a very, very low velocity. So the reason why I'm sharing with you this few real world problems is to tell you that the nature is non-local. There are many problems in nature that can only be modeled using non-local operator. It means that if we have certain complex real world problem. But before I continue, I will share with you some important people that funded fractional calculus. I'm speaking of Leibniz. Leibniz is a great mathematician that everyone knows his achievement, the founder of differentiation and integral calculus, and he is the father of calculus. So when we speak about
Prof, I cannot hear you, but I can see the screen. The slide number 4 with Guillaume Francois Antoine. Bon. Puis Clem, baissez vite. Yeah, Prof.
yes, okay.
Prof Atangana.
Yes.
Hello, Prof. 1 minute.
Yes, I can hear you.
Can you send the slide to Samsung so that he can be moving the slide and you just speak so that it will improve the quality of your sounds? We were not hearing you.
Okay, okay.
You can share send the slide to Samsung. You will be asking him to move forward or to go backward. So you will just only be speaking without sharing your slide.
Okay, please ask him to send me his number, please.
He wrote to you. Okay. I will just send you his email right now.
Okay. So now we are presenting also about another important mathematician, Cauchy, that everybody knows. He is an engineer, a physicist, and he is a pioneer of several branches of mathematics. And he also helped to construct fractional calculus. Then I will present to you Abel. In fact, people believe that from the Abel and the Cauchy work, the fractional integral was able to be constructed. So these are eminent mathematicians that also started the work of fractional calculus. Now, Riemann, everybody knows that Riemann is one of the top mathematicians. He made contribution in many fields, for example, number theory, differential geometry, and we know about the Riemann integral. He also worked on Fourier series. So he worked in many fields of mathematics. And we speak about somebody who is recent, Bell. He's one of the person also who also worked in fractional calculus. He actually introduced a different type of fractional derivative that is also being used in applied mathematics. So I'm presenting to you Professor Capito. In fact, he is one of the person who bring revolution in fractional calculus, because what he did is he was using the fractional calculus suggested by Riemann and Liouville. And what happened is that he was working in a real world situation, and he came out with a different type of fractional calculus that is more natural than the previous one. I'm sure that many people in Africa are saying, so since we have been presenting, you only show people from Europe, from all over. What happened? I decided also to show what somebody from Africa did. So I present to you Abel Atangana, who also contributed a bit in fractional calculus. So it is also good that we show to young African people that we also did something. So I also contributed a bit in fractional calculus. And another important person in the field of fractional calculus is Professor Dimitri, who actually has been very useful to, to recruit many people in fractional calculus, to ask many young people to come in the field and help them in different way. So these are people. There are many other that I did not include, but I included this one such that people understand that there are people in the past that did a lot of work in fractional calculus. There are people in the present that also did a lot of work in fractional calculus, and many people will continue doing a lot of work in fractional calculus. So now I will present to you a very basic mathematical operator. They call it convolution. As you can see in equation 1, a convolution between f and g is written as you can see in equation 1, and the equivalent definition is also given by equation 2. So the reason why I present to you these two definitions, these two formula, is because you will realize that the fractional calculus, the fractional derivative, is also like a convolution. So, but before we jump to convolution, I would like to share with you some application of convolution to see how at which extent fractional calculus can be. For example, in image processing, convolution is considered as a filter, and it plays a very important role. For example, some people would like to know, if you have an image, how do you actually convolute it with a first derivative, second derivative, or you can convolute it with a specific mass to remove noise. Also, in optic, photograph, it is also like a convolution of a sharp image with a lens. So in image processing, also we can speak about image deblurring and image blurring. We can see the application of the convolution in chemistry. We can also see the application of convolution in statistics, in acoustic, again in image processing, digital signal processing. You can also see the application of convolution in electronic. So convolution is a very important operator for fractional calculus. Many people ask the question, what is the physical meaning of the fractional calculus? Is it really useful? If yes, for those who believe that fractional calculus is not useful, you can see that it is a convolution. So the application are in many fields of science. I would like to present to you some definition of fractional derivative. I will start with Capito Fabrizio because the Capito Fabrizio is near classical derivative than fractional, because when you look at the integral associated to Capito Fabrizio, you realize that it is the combination of the first function and the classical integral. So Capito Fabrizio derivative that was suggested in 90, 90, I think 5 years ago. It is a convolution of a first derivative and exponential function, but that exponential function has what they call delta Dirac property. It means that when alpha is equal to 1, equation 3 will give us the classical derivative. If alpha is equal to 0, then we are going to obtain the function itself. This derivative was introduced. Why? Because Capito, who is the founder of Capito derivative, realized that people misuse his operator because his operator is based on the power law, and people apply it in all the field. People apply it even when the data does not show the power law, pattern. So he said, no, the nature is not only the power law. So he suggested a new derivative that is a convolution of a first derivative and exponential decay function. And what is important is that that kernel is non-singular. It means that we are living the classical way of differentiation, fractional differentiation. So another definition, which is more older, is the Capito derivative, which I like because it is a convolution of the first derivative and the power law function. It means that in this case, this type of derivative is very useful when you are dealing with processes exhibiting power law behavior. But the Capito Fabrizio is very useful when you are dealing with a process that exhibits exponential decay behavior. Now, what happened is that when the Capito Fabrizio derivative was introduced, some people said, no, the integral is classical. Then I decided to actually come out with something that is different, that is non-singular also, like Capito Fabrizio, but that should have some fractional behavior. Then I searched and I realized that the exponential function is actually the particular case of the generalized Mittag-Lefleur function. So I define with Professor Dimitri, I define, if we can go down, I define a differential operator that is, I define a differential operator that is a convolution of the first derivative and the power law. So this is very important here because the Mittag-Lefleur function is a specific function that has application in many real-world problem. For example, the Q system. For example, in statistics, we have Mittag-Lefleur distribution that is actually used for super statistics. So I was able to define then what they call today Atangana-Baleno derivative.
Prof,
There are
sorry, the slide is not following.
People that said, oh, Atangana, the Baleno derivative, yes.
Be careful with the slide. Sometimes there is a delay.
Can you see now?
Yes, yes.
Okay. Okay, so this is the Atangana-Baleno fractional derivative in Capito sense. I like the Capito sense because it was constructed using real-world problem. Of course, the Riemann version is very important in theory, also in application. But some people used to ask the question, when you apply the Laplace transform, you obtain unusual initial condition. How do you give the interpretation for those type of initial condition? Then some people say that it is applicable in diffusion. Other people say that it is applicable in other field. But when you use the Capito version, obviously you can see that it is the convolution of the first derivative and a kernel, which is actually by applying the Laplace transform, you are able to capture the usual initial condition. So I would like to go back a little bit up here. When the ABC derivative was constructed, it was applied in many fields. Many people start using it. There is a paper written by some Italian mathematician where they say that ABC does not add any new thing in the field of fractional calculus. In fact, they say that it is the capital derivative. So in this theorem, I proved that no, ABC is actually the convolution of the capital derivative and the Mittag-Leffler function. So if you apply the Laplace transform on the ABC derivative, you will realize that by applying the Laplace transform here inside here, if you can see, you will realize that this and this is actually what they call the Laplace transform of the capital derivative. So if you apply the Laplace transform of the capital derivative and you take the inverse, you will realize that the ABC derivative is giving you the convolution of the capital derivative with power law and the generalized Mittag-Leffler function. So if actually alpha is equal to 1, you can also go back to the classical derivative. But when alpha is different from 1, you are above capital classical derivative, because the Mittag-Leffler function that was used as a kernel is actually exponential function when we have a small term. But for the later term, we have that the ABC, the Mittag-Leffler function is exactly the power law. So you are able to capture capital Fabrizio for earlier term and capital derivative in later term. So I prove that. Then when I come here, I show you the kernel that I presented before. For Riemann Liouville, we have the power law function. For capital Fabrizio, we have the exponential decay function. But for ABC, we have the Mittag-Leffler function. So there is a study done by some mathematician from Brazil. They try to see the difference between these three differential operators. So they took the kernel and they tried to do some analysis. Then if you go here, you will realize that they found out that the weighted term distribution for ABC, it is with the red. For Riemann Liouville, it is with the blue. And for the Brownian motion, that is a very well-known concept, it is with green. Then we realize that for a small time, the ABC is the same term like the Brownian motion, but for the later term, the ABC is almost the same term like Riemann Liouville derivative. So what does that mean? It means that the ABC derivative is able to capture at the same time the Brownian motion, and it has a crossover to Riemann Liouville due to the power law behavior. Then they presented also the mean square displacement. Here they compare the Riemann Liouville, the capital Fabrizio, the Atangana Balwenu, and the Brownian motion. You will see that for the earlier term, let us say 10 power 0, what we have here is that the ABC is able to capture at the same time capital Fabrizio and the Brownian motion. Why? It is very simple to understand, because the Mittag-Leffler function can be approximated to exponential function for small time, and it cannot be approximated to power law for a later time. That is why the mean square displacement for ABC is actually capturing the capital Fabrizio and the Brownian motion, and also the Riemann Liouville. So if you continue, you will see the probability distribution. We have figure 8. the Riemann, we have figure B, the capital Fabrizio, and we have figure C, the Atangana Baleno, and we have figure D, the Brownian motion. Then the analysis shows that also there is a crossover with the ABC derivative that crosses from capital Fabrizio, Brownian motion to Riemann Liouville derivative. Then they summarize it. By summarizing, they realize that the waiting time distribution for Riemann Liouville is the power law, and the mean square displacement is the power law and scale invariant. However, for the probability distribution, we have non-Gaussian. That is the long tail that we always observe with the power law. But with the capital Fabrizio, we have exponential function. But this is important because the mean square displacement is a crossover from the usual to confined division. And now the probability distribution is a crossover from the Gaussian to non-Gaussian with a steady state. Very important. Why? Because there are some real world problems that start and stop and start again when there is no external force. But here the capital Fabrizio is able to exhibit such behavior, which is very important. Now the ABC version is the waiting time distribution is a crossover from the stretch exponential to power law, whereas the mean square displacement is the crossover from usual to subdivision. Here we don't speak about confined. Here the space, the subdivision just means we go very slowly, but we can cross the border. Now the cross over from Gaussian to non-Gaussian is the probability distribution. So I'm sharing with you this part to see the importance of each fractional derivative and when it can be applied, because some people knows without knowing which one is applicable for which problem. So here it describes to us actually when and how we can use the different fractional derivative. All of them are very important because there are many real world problems that exhibit power law. Those problems can be solved using the Riemann. And there are also many real world problems that exhibit a crossover from usual to confined division. Those ones can be solved using the capital Fabrizio. There are also many real world problems that exhibit crossover from waiting time distribution to probability distribution. Those ones can be solved using the Atangana Baleno. So one of the important things here is that the nature is explaining to us that mathematics was created by human to understand nature. When it's that our mathematics should obey God law because God nature. It means that our mathematics should not give condition that will not be applicable in the real world. So all those fractional derivatives are very important, and all of them, the one that has been presented so far, are not able to solve all the problems that we have. So it means that in the future, we are going to see many different fractional derivatives that will also be useful. So there is no limit. It is not a limit here to say that no, we cannot come up with another fractional derivative because the reason is nature is complex and we need many serious mathematical tools to solve those problems. So now I'm very skilled to present to you the commutativity and the limitation of the commutativity. We all know that if I take an operator, maybe dot, and I have an element A and B, if A, B is equal to BA, then we can say that the operator is commutative. But you will realize with me that in many real world problems, the commutativity does not apply. And also, the commutativity shows us some weakness. I will share with you some important development in mathematics that was obtained using non-commutative operator. Let me start with the Strong-Digger formula. That one is complicated for some people, but let us go to a very simple operator that everybody knows. When we have R plus the real the positive real axis of real number, and we have the operator plus. If we take 2 plus 3, we are going to have 3 plus 2. This is okay, but we stay in the same positive part of R. But is it possible for us to describe the whole R using the plus operator? I may say no. Why? Because if we only consider the commutativity, we will be having a problem of 0 minus 1. We obtain minus 1, or we'll ask, what is this? Now, when you compare the operator plus and the operator minus, you take 3 and 2, you realize that 3 minus 2, you have one that belongs to the R plus, and 2 minus 3 is equal to minus 1. We cross and we go to R minus, which is very important to describe the whole real world, the real number. So we have the division operator. You have 1 divided by 2 is not 2 divided by 1. But because of this division, we are able to have a larger space. We have also the logic of the truth function. We have the cross product. We have the multiplication of the matrix. I can also speak about the Lie bracket of the Lie algebra. So we can go on. I present to you many operator that need to be non-commutative for us to obtain serious space. So what is happening here is that they are among those differential operators that I show you, some they don't actually satisfy what they call index law, and other one they satisfy the index law. But I'm going to show to you the difference between, to take a non-commutative operator. We are going to see that if I take alpha as a fractional order and the beta and the fractional order, if I take, for example, the derivative of order B of the derivative of order alpha or the derivative of order B, I will not be able to obtain the derivative of order beta of the derivative of order alpha. I'm not going to obtain it. Is it really a weakness or is it important? Nature is telling us that this is important. Why? Because if I take an example, Professor Mama is a teacher. Let us say that Professor Mama is teaching fractional calculus, or Professor Gomez or Dr. Seda or anyone, is a teacher. So we have one student, for example. If Atangana teach first fractional calculus to the student, then Professor Mama come and teach that same student fractional calculus, I'm pretty sure that is not going to have the same impact like when Professor Mama start teaching, then Professor Atangana come and teach also at the end. The impact will be different, showing non-commutativity in nature. So if you take, for example, alpha that belongs to 0, 1, and you compute the derivative of order alpha or the derivative of order alpha, no problem. We are going to obtain the commutativity. And this is what they call diagonal. And this diagonal is like a frontier. Yes, something like that. I don't know whether it is English, but it's like a frontier. But what is happening here is that I would like to actually obtain a specific matrix to see what is the application, what is the importance of being commutative and non-commutative as an operator. So if you take this a square matrix, everything is okay. Then you try to find the determinant of this matrix. Now, if we have commutativity, that means if obviously that the determinant is equal to 0, that means the matrix is not invertible. It means that I cannot go back in the past. It means that I cannot go back where I'm coming from. However, if the matrix is non, if the operator is non-commutative, we are going to see that the determinant is different from 0. What does that mean? If the matrix A with the inverse is going to give me the frontier, the opportunity to go back to the initial state. It means that I go back where I was coming from. So what is happening here is that with this operator, it is not frontier. Whereas if you have an operator that is only commutative, you will not be able to go back to the past. Therefore, you lost the memory. So having non-commutativity is very important. It allows us to have a bigger space. It allows us to capture many real-world problems. Like I showed you before that, with ABC, you are able to cross exponential to the power law. This is very important because the real-world problem that is different behavior. So if you have an option to cross over, so we have a fractional integral, we have the Riemann Liouville integral, and we have the Capito-Fabrizio integral, and we have the ABC integral. And now there is a question I always ask myself as a fractional calculus worker or somebody who is working in the field of fractional calculus. We have two types of derivative. The Capito type, that is the derivative, the convolution of the derivative of a specific kernel. And we have a second type of fractional derivative, that is the Riemann version. And the Riemann version is the derivative of the convolution of the function and a specific kernel. Now, when you look at the literature, you will realize that we have two types of fractional differential operator, but we have only one type of a fractional integral. And the question is, how can we then apply the fundamental theorem of calculus with for both? It cannot work. Then, in one of my papers, I discussed about the fractional integral. And I also know that Professor Rifai from Jordan, if I'm not mistaken, he did produce a new fractional integral that will be the inverse of capital derivative integral. So in one of my work, I did that proof. And I suggested that capital integral should be the Riemann integral plus a function. Capital Fabrizio integral should be the normal capital integral plus a function. And ABC should be the normal ABC integral in a Riemann sense plus a function. Why this function? This function is a memory function. It is very important because when you look at the difference between capital derivative and the Riemann derivative, you will realize that capital derivative has an integral structure, whereas the Riemann-Liouville derivative has a derivative structure. Then it is important for us to know that the fundamental theorem of calculus or fractional calculus will be only achieved if capital derivative has a specific associate capital integral, and this will be we will be able to achieve what we want to achieve. So for the fundamental theorem of calculus, you apply the capital integral in Riemann, you obtain equation 26. But now, to satisfy the fundamental theorem of calculus, you will need that the capital of that function that are suggested now should be what is happening in 26. Derivative to the capital integral, you will find exactly the function which give us the fundamental theorem of calculus. Now, you do it also for capital Fabrizio derivatives, we obtain the same thing. So I tried to prove using the Cauchy the general fractional Cauchy problem with capital derivative. I was able to prove that the fundamental theorem of calculus is reached. You see that here we obtain again equation 34. So this is important for us to not be misled. We have capital derivative, you should have capital integral. Riemann type derivative, you should have Riemann type integral. So the fundamental theorem of calculus will only be applicable between capital derivative type and capital integral type, Riemann derivative type and Riemann derivative, Riemann integral type. Very important for us to know. So I thank Professor Nieto for his work that he did recently. I also thank Professor Rifai from Jordan for his excellent work also that he did to tell people that we cannot have two types of derivative, but we have one integral. So some people ask me, can you actually give us a specific function, Phi, the capital function of memory? Can you actually give it? So there is a very important work that was done by a Brazilian, and I show you already some of their work. So they proved that the kernel associated to capital Fabrizio has a crossover effect in terms of the mean square displacement and also the probability distribution. So this implies that there exists a constant term, TA. The capital Fabrizio depict usual diffusion. So after that time, the capital Fabrizio integral will depict what they call confined diffusion. So the memory is what is like piecewise. It is a piecewise function. So that piecewise function, of course, when it is we are at 0, it's supposed to be 0 because the capital in derivative has a full memory. It has a beginning and it has the end. They always say in the world that everything has a beginning and everything has an end. So non-singular kernel, they are important because there are some problems that have the beginning and the ABC derivative or Atangana derivative. So in the case of capital Fabrizio, I discovered this function, but the derivative of that function, equation 39. What I will do now is I will calculate the capital Fabrizio derivative of that function, and I will show you that it gives the result. Capital Fabrizio derivative require that the function should be differentiable like equation 39. So by doing it, by working everything out, I was able to find F0 exponential. So the capital integral for capital Fabrizio derivative exists and it has a memory function. If you apply the fundamental theorem of fractional calculus with that, you are going to obtain the desired result. So if you read in any paper where people say a capital Fabrizio derivative does not satisfy the fundamental theorem of fractional calculus, it's because those people use the Riemann integral version and the capital Fabrizio derivative that is in capital sense, and they wanted to satisfy the fundamental theorem of calculus. You cannot actually mix potato and yam. These are two different things. So potato should be with potato, yam should be with yam for you to have the desired result. And for the classical derivative, that function is a constant. You can calculate actually the memory function. You are going to obtain that the function, and if you do it with required. And here I would like to show the difference between those kernels and the connection in statistics. This is important because the fractional derivative, according to Riemann Liouville, is actually having the kernel that is the power law. And in the theory of probability distribution, that distribution is associated to the Pareto distribution. And the Pareto distribution has some advantage, and that I'm not going to actually is that able to produce result while the fractional order variable, for example, if you have of 80 and 20, tend to agree with a large when you look at the Mittag-Leffler, the ABC kernel, when you look at the Mittag-Leffler kernel, you realize that it is what they call Mittag-Leffler distribution. And this Mittag-Leffler distribution was known to be applied in many real world problems, because when the alpha is equal to 1, we can recover the normal Poisson distribution. When alpha is different from 1, we can obtain this what they call super statistic. Then when you go on, you try to calculate for example some distribution as a really? Can you see? Hello? Can you see now?
Yes,
we can
now.
Can you see? Yes, thank you. So,
Yes, we see.
thank you. So for that, for the Riemann Liouville is one. If you do with about derivative, you're going to obtain equation. It's what we call the statistic arrival time. So I calculated also the arrival time of the kernel associated to ABC derivative. You will have equation 53. So there's another one they call the moment for the Riemann, we are going to obtain equation 54, equation 55. So the mean, like the average, if you can say like that, the average for Riemann Liouville is infinite when alpha is less than 1. And this is actually where the capital for the Riemann Liouville derivative lie for process So we take a general Cauchy problem with capital. We take the general Cauchy problem with the capital Fabrizio derivative. Then we try to actually solve it numerically. By solving it numerically, what we do is we take it at t equal to k plus 1. Then we have a question 61. Then we take also a k. Then we have a equation 62. Then we do equation 61 minus equation 62. Then we have equation 63. Since the integral, it is we don't have no linearity here. We can then have from k tk to tk plus 1. Then the function h tau u tau can be actually interpolated using the Lagrange polynomial or the Newton polynomial. If you use the Newton polynomial, for example, you obtain equation 64. By doing the integration, you obtain lastly equation 65. So you can use this numerical approximation to solve it numerically. It has some advantage, some limitation, and so as all the numerical scheme, so no problem. Then if you work everything together, then you will obtain the final scheme that is equation 67. Then if you also take with capital derivative, what you will do, only you take a t k plus 1, then you have equation 70, then you replace the function before you replace the function h by the polynomial interpolation, you take the sum to capture the non-linearity, locality as in equation 71. Then you replace now h by a polynomial. You replace h by a polynomial, Newton polynomial. You obtain equation 72. Then if you integrate very well equation here. Equation 76. So now I would like to cross over to go in something different, but I will mix those things then come back to fractals. me Professor to fit what they call a Trinitron. Trinitron, I call it Trinitron because of 3 dimensions. So in the Trinitron, we have 2 imaginary parts and 1 real real part. So if you do the addition, you do the multiplication, then this is what you have a question 7 for multiplication. We have a question 86 for addition. No problem, but the problem is that this does not follow the classical normal complex number like associativity. There is no associativity here, which is not a weakness. So what we have, like the Julia said, here I also represent something similar to the Julia set in the Trinitron. Represent the Julia set then if you change again the parameter, you obtain this figure here. By changing again, I consider what I call it African tornado mapping, equation 90. If you plot it, you're going to obtain this type of figure that you see here. So now what you do now is you try to take fractional fractal that I have shown before and the fractional calculus, then you try to put them together and see what you can do. So if you take, for example, the Julia mapping in the normal complex number that everybody knows, then this is what you obtain, like the Julia the fractal. But if you combine that fractal, I would like to see if I can reproduce the lung of a human being. So I create an algorithm here. Xi is equal to this, and yi is equal to this, as you can see here in equation 93. Then I create a small algorithm here. After creating this small algorithm, I put those things together. I obtain this figure here. I obtain this figure. You see, it look like a long heart. I obtain this. So if I change again with a different chaotic mapping, I obtain something like this, as you can see here. Then if I change again with a different one, then you can obtain something different. Then now, the last part of my slides is what they call global differentiation and integration. Why global? Is because normally we know that the rate of change between A and B is f of A minus f of B divided by A minus B. And if A tends to B, if the function is differentiable, we have what they call classical derivative. And one day I asked myself, what if the function that is down is different to t? So what if it is a general function, but that general function will have specific condition? For example, the derivative is greater than 0 and the function is increasing. So I define something like this, equation 94. Then I can capture all the rest that we know in the classical differentiation, as you can see. Then if G is equal to T, we have the classical differentiation that you know. If T is equal to alpha, we have the fractal derivative that is in the literature. If, for example, G is equal to this, you obtain equation 100 that myself and Professor Mbufo, another Cameroonian, we did. If G is equal to T beta, then you can obtain this one. Of course, that this is the fractional variable order. Then by doing all these things together, if for example, G is also differentiable in the classical way, we are able to obtain 102. The reason why I present this part is because there are some people in the literature, they say conformable derivative is not a derivative. But what is very important here is that the conformable derivative, which is one class of global derivative, is connected to the well-known Riemann-Stieltjes integral that is known by everyone as the more general integral. So the conformable derivative is actually a derivative that is associated to the Stieltjes Riemann integral that I'm presenting in equation 106. This integral is known by everyone. If the function j is, for example, t, you are going to obtain the classical integral. So this version is more general than the normal classical integral. So you can actually construct a global fractional differential operator with power law equation 108, equation 109 with, in a Riemann sense, the first one capital sense. So in a capital sense, if we have that the function is differentiable, you can have this. So you can go on, find the integral associated to each of one of them. Then you can also, for ABC case, you can find the integral associated to it. Then from there, if you take a specific version of what I presented you up there, like that, the derivative is the classical fractal version, then you are able to have what they call fractional derivative, equation 116. You can find the integral equation 117. Then you continue down, you go for capital version, you can do that. You find the derivative, you can also find the integral associated to it. Then for ABC, you can find also the derivative and the fractional derivative associated to it. Then I will show you some application of non-local operator. For example, if I take the 3D tornado that I showed you before, I'm able to obtain this, but now I'm using fractal fractional version. If I increase it a bit, I'm able to obtain this figure that is here. If I increase it again more, I can obtain something different. So I take another model in the Commutativity. If you play a bit more, you are able to obtain this figure here. So if you go further, you can increase it to obtain something different. So I also put together a COVID-19 model with 9 classes. I solve it using the numerical scheme that I showed you before. Take some initial condition, like for example, in South Africa, you can say that we have 800,000 people that are susceptible, 3 people that are infected. Then you take all these parameters, when we build them together, with no lockdown, we see that everything is increasing. With lockdown, you see that everything is decreasing. Of course, that we can be in lockdown, but also if people are not behaving very well, the COVID will spread. But what is important is that the COVID is not having leg. It's only moving if we move. So if we are not moving, the COVID rate also will go down. So I try also to fit that model using experimental data. Then I obtain this here. The prediction is in blue, and the data collected are in red. So this is my presentation. I can show you some references that I used to build this presentation, and all these are the references. Then thank you for your attention. The reason why I put at the end Africa we raise is because most of the time Africa is marginalized. For example, now the COVID is out. The vaccine that are in Africa, maybe only 2% of all African people are vaccinated. So I pray that one day God will give Africa its original glory, because what I know is that when people from the other side they came in Africa, Africa was actually a wealthy country. It was a place where people were also working hard. It was a place where people developed a lot of mathematics. But nowadays, we are unable to show to our kids that this formula was generated by a mathematician from Africa. So that is why I'm praying God that He should help Africa to rise again, so that all our friends around the world should also be happy to say this was introduced by an African person. Thank you very much.
I'm clapping. Thank you very much, despite all the disconnections. Sure. Prof Mama, do you have time, Prof Atangana, for questions?
Yes.
Okay, good. Yeah, let's have questions if you have any. I have asked people to type something in the chat, but not many. Let me see if there's any question there currently. No, so a lot of people are saying nice presentation. Thank you. We wish we didn't have the internet problem. Definitely, this is an interesting topic to many people, and many people showed up anyway. So, any questions?
Hi, Bubakar. There's a hand from Hasi.
Okay, go ahead. Unmute yourself and say something.
Professor, say something.
Okay, Professor Abdul Atangana, I really appreciate it, and I really want to say thank you for your such a kind and informative information about the fractional calculus history, and such a kind, very hot topic is really important for developing the sciences, and also science, nonlinear science, especially in the recently. And many applications directed and their future in this sense. So anyway, I would like to thank you very much for your nice and excellent presentations. Thank you.
Thank you very much, Professor Ajik. I would like to add a comment on what you said, because there are some people saying that fractional calculus cannot solve a problem.
Yes, absolutely, yes.
But what is important is that we realize that the world is non-local. People like Professor Luis Cavalieri is a field medal that is working in fractional calculus. So if somebody said fractional calculus cannot actually solve a fundamental problem, that means the person have not read and have not worked in fractional calculus. That is a very misleading, a misleading statement that somebody can tell to students. Fractional calculus is very important. It was initiated by top mathematician, outstanding mathematician that perhaps no one of our age have achieved what they have achieved. They initiated it because they realized that the world is non-local. So thank you, Professor Ajik.
Thank you, Professor. Thank you so much.
Thank you to both of you. And there is Etienne Wamba who wants to also ask a question or make a comment. Go ahead, Etienne, unmute yourself.
Afternoon, everyone. Can you hear me, please?
Yes, we can hear you.
Okay, Prof Atangana, that was a very nice talk. I really like it. I'm not actually a mathematician, but I'm interested in the fractional derivative since it is very important in physics, especially in the case of optical fibers and also in nanomaterials. So my question is this. On doing what we call imaginary time propagation, we need to Fourier transform, let's say, some quantities. And my question is whether you use, let's say, the Riemann Liouville or the Caputo, how do you call it? The Caputo, anyway. Yeah, Riemann Liouville, Caputo, oh, sorry, it was Caputo Fabrizio, yes.
Yes.
And Atangana Baleanu fractional derivatives operators. Do we have any difference in the Fourier transform?
Yes, you see, when you look at the Laplace transform, let us take the Laplace transform, for example.
Yes.
You will realize that the Laplace transform of Riemann Liouville is different from the Laplace transform of Capito Fabrizio, and it is also different from the Laplace transform of the APC derivative. So if you apply Fourier transform, I will send you some paper where I did with Fourier transform. You will see that the Fourier transform are different also. Because remember the fundamental theorem of convolution. If you have convolution of A and B, then you apply the Fourier transform. It's going to give the Fourier transform of B V and multiply by the Fourier transform of B. So now, if the kernel are different, you are going to obtain something different, because what you have here is that Capito Fabrizio is the convolution of the first derivative at exponential kernel. So the Fourier transform of exponential kernel is different from the Fourier transform of power law and different from the Fourier transform of mechanical function. Thank you.
Okay, but now let's say a subsequent question can be this. You know,
yes.
In general, you work on, let's say, concrete quantities in physics. Now, what happens if, let's say, I take one of those derivatives and then I apply, let's say, I Fourier transform, let's say, a quantity, and then I Fourier transform back. I mean, in the three cases, I mean, from what you are saying, I might obtain different quantities. So in this case, how am I going to understand, let's say, the consequence on the, let's say, on the physical nature of my problem I'm solving?
You see, this is the big problem we have nowadays. The big problem is that we just replace a derivative by classical derivative or with any fractional derivative. It should not be like that. You have experimental data, you plot your experimental data. The reason why we have model is because we want to see some parameter that fits with the experimental data. So you plot your experimental data, you're going to see that your experimental data has, for example, the power law behavior, or it has, for example, a crossover behavior, or it has, for example, the decay behavior. So if you have, for example, the power law behavior, you know directly that capital derivative is well applicable. If it has exponential decay behavior, you know that capital Fabrizio is tweakable.
Okay, thank you very much, Prof. So you mean whenever you want to use, let's say, a given derivative, fractional derivative, we always have to run some kind of preliminary test to see which kind of operator qualify for our model.
Yes, if you have data, because if you are doing just mathematics, you can do many theorems, many formula, no problem. But if you have real data, the data have to guide you which kernel is suitable for this problem.
Okay, thank you very much. I'm satisfied. Okay.
Thank you, thank you. We have another hand raised, Ibrahim Nali. Can you unmute yourself and talk? Etienne, can you mute?
Hello, teacher.
Okay, Ibrahim
Hello,
Nahil.
you hear me?
Yes, go ahead.
Teacher, first of all, thank you, Professor, for giving me this chance to attend your presentation and ask my question. So my question is, what's the foremost advantage of fractional derivative as compared to other fractional derivative?
You say?
What's the foremost advantage of fractional derivative as compared to other fractional derivative?
Okay, what happened is that, you see, I have that the Riemann-Liouville derivative is actually the classical derivative of a convolution of a function and a specific kernel. So in the literature, there is what Professor Wen said, fractal derivative. And the fractal derivative I presented it earlier. So what I did is, I said, what if I replace the classical derivative with the fractal derivative? So if I replace it, then my operator now is going to have two order, the fractal dimension and the fractional order. What happened is that if, for example, beta that is representing the fractal is equal to 1, we will obtain again the fractional, all the fractional derivative. But if the fractional order is equal to, for example, 0, is equal to 1, I will be able to obtain the fractal, if I can call it fractal integral. So the advantage, I can't say the advantage, the only advantage here is that we have two order that can be manipulated to capture heterogeneity or complexity of nature. So you can see that the last figure that I show you, you are able to have something that repeats itself.
Yes, yes, teacher. Yes, I understand you. Thank you so much.
Thank you.
All right, thank you very much. I think we should let you go and enjoy your holiday now. We've taken too much of your time. Thank you very much. It's really appreciated. And yeah, we should all thank the speaker, unmute and thank the speaker one more time. Okay, and that's it. We'll send emails and invitation for our next talk.
Okay, bye.
Thanks, Prof. Bye.